Have you ever really stopped to think about why numbers work the way they do? I mean, we use them every single day, right? But underneath it all, they're governed by this hidden set of rules, unbreakable rules that we just completely take for granted. So let's dive in and really uncover the architecture of our entire number system. It all kicks off with a question that sounds so simple. You probably haven't thought about it since you were a kid. Why is 5 times 3 the exact same thing as 3 times 5? We just know it's true, it's baked into our brains. But is that just some random happy coincidence? Or is there something much, much more profound going on? Well, spoiler alert. It is absolutely not a coincidence. It's a rule. It's a fundamental principle that we've all sort of agreed on. In fact, the whole world of mathematics, from adding up your groceries to calculating the orbit of a planet, is built on just a handful of these foundational rules. Mathematicians call them axioms. And they're the bedrock that makes our world of numbers stable, predictable, and, not total chaos. But what happens when those rules just aren't enough? See, for a really long time, mathematicians thought they had a pretty perfect, complete system. And then they found a glitch, a paradox hiding in plain sight that threatened to bring the whole thing crashing down. Okay, so let's start with the world as they knew it. This was the world of rational numbers. Now that sounds fancy, but it just means any number you can write as a simple fraction. 1/2, -7/3, even a whole number like 5, because that's just 5 over 1. And this system is incredibly powerful. You can add them, subtract them, multiply, divide, and you always end up with another rational number. It feels totally sealed, totally complete. And for centuries, this seemed to be the whole story. Rational numbers could measure anything, calculate anything. What else could you possibly need? But then, the ancient Greeks were just messing around with one of the simplest shapes imaginable, a square with sides of length 1. And when they looked at the diagonal, they found something that completely blew their minds, a length they literally could not write down as a fraction. It was like they had discovered a shocking, terrifying black hole on their number line. The way they proved this is it's a beautiful piece of logic. It's called a proof by contradiction. So you start by saying, okay, let's pretend the opposite is true. Let's assume the square root of 2 can be a fraction, a over b, and that we've simplified it all the way down. Well, if you follow the steps, you square both sides, and you find that a has to be an even number. But then if you plug that back in, you find that b also has to be an even number. And wait a second, if both a and b are even, then the fraction wasn't in its simplest form. You could have divided by 2. That's a contradiction. The whole starting assumption just completely falls apart. It proves, without a doubt, that the square root of 2 just cannot exist in the world of fractions. It's a ghost in the machine, a total glitch. And this was not a small problem. As our source material points out, it was literally impossible to fix this with the rules they had at the time. Their existing tools, the basic rules of algebra and order, they just weren't powerful enough to explain how a number like the square root of 2 could even exist. They needed something new. So it was back to the drawing board. Mathematicians had to build a new, more robust set of rules, a complete set of axioms that could handle these weird new irrational numbers, and build a number system that was truly seamless and continuous. And what's so cool here is how elegant and symmetrical these rules are. Take a look. For both adding and multiplying, you have what's called an identity element. That's a number that basically does nothing. For addition, it's 0. For multiplication, it's 1. Simple enough. And for both, you also have an inverse, something that gets you right back to that identity. For addition, it's the negative number. For multiplication, it's the reciprocal, 1 over the number. It's this beautiful mirrored structure that lets us do all the algebra we know and love. Then you've got the properties that let us basically rearrange the furniture in an equation. The commutative property. That's our 5 plus 3 equals 3 plus 5 rule. Associative just says it doesn't matter how you group things. And distributive, that's the one that connects addition and multiplication. These are the workhorses of algebra, the tools that let you shuffle all the pieces of an equation around without breaking anything. But numbers aren't just about algebra, right? They're also about order. And this is where the rules of inequality come in. And honestly, the most important one is the trichotomy law. It's an incredibly strict rule. Think about it. For any two numbers you pick off the number line, one and only one of 3 things can possibly be true. The first is less than the second, they're equal, or the first is greater. That's it. There are no other options, no gray areas. This law is what gives our number line its rigid, unambiguous backbone. Okay, so we've got rules for algebra and rules for order, but we still have that annoying hole where the square root of 2 is supposed to be.
These rules are great, but they don't fix the glitch on their own. We need one more, a final master axiom, the master key that unlocks everything. And this is the big one, the completeness axiom. Now, it sounds a little abstract, but the idea is actually super intuitive and powerful. Imagine you take a pair of scissors and you cut the entire number line in two. You put every number to the left of your cut in a pile called set A and every number to the right in set B. The completeness axiom guarantees, it promises, that there has to be one single number, z, that defines that cut. What it's really saying is there are no gaps. Period.
Because before this axiom, that number line wasn't really a line at all. The rational number line is more like a sieve. It looks solid from a distance, but it's actually filled with an infinite number of tiny, invisible holes. And one of those holes is exactly where the square root of 2 is supposed to be. You can get infinitely close with fractions from either side, but you can never, ever actually land on it. And this is the fix. The completeness axiom comes in and plugs every single one of those holes. It turns that sieve into a solid, continuous line. It guarantees that a number like the square root of 2 has a precise, exact location, finally filling that gap and giving us what we now call the complete set of real numbers. All right, so we plugged the gaps. We've built this perfect, complete set of rules for our numbers. But so what? Why does this actually matter? Why did we go to all this trouble just to find a home for the square root of 2? It matters because this whole journey took us from a broken, gappy system, the rationals, to a system that is perfectly continuous and complete, the real numbers. And that jump from a collection of disconnected points to a smooth, unbroken line is honestly one of the most important breakthroughs in the entire history of human thought.
And the consequences are just enormous. I mean, without a complete continuous number line, you cannot have calculus. Simple as that. Calculus is the language of change, and it completely depends on being able to zoom in on a line forever without ever falling into a gap. And without calculus, forget about modern physics, engineering, or economics. This one single rule, this one axiom, underpins our entire ability to mathematically model the world around us. It is, and this is no exaggeration, the foundation of modern science. So the next time you use a number, just remember the incredibly elegant and powerful rules holding it all together. These axioms, they aren't just descriptions of how numbers work. They're the actual blueprints we use to build our reality, which kind of leaves you with a fascinating final thought, doesn't it? These particular rules built our mathematical world. What other strange and beautiful realities could we build if we just started with a different set of rules?